Okay, good evening, folks. How's everybody doing tonight?
Hello, hola, privet, nihama, etc. I'm doing okay.
All right, that's good to hear, Ian. How's everybody else doing?
Good.
Happy Monday. Happy Monday. It's hard to believe that we only have, after tonight, 3 more classes. 3 more classes until the semester's over. That's pretty wild. Just to touch on a couple of things, let's make sure that we're still on top of our discussion posts. Those will get graded and you'll get those grades back to you soon. You have your first draft of your space mission assignment due on Friday. I don't know how many of you actually got a chance to watch the lecture from earlier today, but if you did, you will have heard my strong request that your drafts are submitted on time, because I need to make sure that I have the time to grade them and give you feedback. That way you can make any necessary changes before you actually give the full-on presentation. And if you don't have it in on time, I can't promise that I'll be able to get to it, because I only have certain time in my hours in my week that I have free to get that done. So please make sure that you are prepared. If you have any questions, I'm happy to answer them at the end of class. So we're going to be giving those presentations during our last lecture. So next Monday and the following Monday are going to be our last instructional days, all right, where we're going through slides together. Okay, so let's get started. I'm going to screen share here. We are on lecture 9.2. Looks like we've got ourselves a student in the waiting room. There we go. All right, lecture 9.2. So earlier in the last session, we started to talk about the so some of the important properties of stars that we're going to be looking at, such as luminosity, temperature, spectral type, apparent brightness. Right, some of those are intrinsic to the star, others are not. And finally, what we're going to bring into, or we're going to bring our attention to, is mass, because mass is one of the most important quantities to be analyzing when you're looking at stars and you're trying to study them. Okay, so how do we measure mass from binary star systems? We talked about how you could measure the how you could measure mass when you have orbiting bodies, and as it turns out, just about half, somewhere around there, half of all stars are in binary star systems, right? Our sun is not in a binary star system. Binary star systems meaning we have 2 stars that are orbiting each other. All right, and so we have 3 types of binary star systems that we're going to be looking at over these next few slides. The first is a visual binary. Right, so a visual binary is essentially when we're looking at 2 stars and we can look down on the plane that they are orbiting each other in. So for example, I have a piece of paper here, right? If the stars are orbiting each other, if they're both orbiting on this plane, then from your perspective, you can see a visual binary. If the stars are orbiting in the plane of the paper, but from your perspective, you're seeing the plane like this, you're not really able to capture the binary system the same way, right? And so for something to be a visual binary system, we need to directly be able to observe the motion of both stars. And you can see here on the PowerPoint slide, there are two stars, stars A and B. A is the larger one, B is the smaller one. And we're looking at a snapshot of these two stars, or several snapshots over the course of about 70 or 80 years. 70 years, excuse me. All right, so going from 1900 to 1970. And you can see how star A is, in the first picture on the top left, and star B is on the bottom right. And then in the next image 10 years later, star A has shifted a bit, right? Going clockwise around from this perspective. Star B has also gone a little bit around. And then they both sort of continue on their way. There we go. See, they're getting a little bit closer together. Right, that orbit gets tighter and tighter. And then they swing around each other. Oop, that one got a little crazy. And based on this, it looks like, let me actually erase my drawings. May have gotten a little bit carried away with my my drawings there. Let's just erase all that. If you're trying to figure out, looking at these images, about how long does it take for the two stars to orbit each other? If you're comparing to the year 1900, which of the subsequent images looks like it best matches that first image? Jerain, which one do you think best matches the year 1900?
Hold on, I'm trying. It looks a little tricky.
Okay, well, so we're looking for a picture where A is on the top left and B is sort of on the bottom right.
I was gonna say 1950.
Yeah, I'd say 1950 also. Right, 1950. So from 1900 to 1950, that's about how long it takes for full orbit, somewhere around 50 years. Right, so in this case, we're seeing an orbital period of about 50 years. 50 years. All right, so we can tell that from a visual binary, right? We can look directly at it and figure out how long it takes for these two stars to orbit each other. Then we have an eclipsing binary. Now we saw, something similar to this when we were looking at the exploration and the discoveries of exoplanets. All right, we saw on that NASA simulation that if an exoplanet passes or transits in front of a star, right, we can figure out the size of the exoplanet based on its brightness, or the changing in the brightness of the star. And this is a graph plotting something very similar, right? We're looking at time on the x-axis and apparent brightness on the y-axis, right? And let's just look at this underneath each picture and sort of make sense of what we're seeing here. Right, so in the first image, we have star A, what's called the red one. The orange one is star A, the blue one is star B. So we can see star A and star B. And so from our Earth perspective, we would be detecting the full brightness of both stars. And that's what we're seeing here. Right, fast forward a little bit. It looks like the star B is orbiting around star A in a counterclockwise fashion from this perspective. Right, so when star B gets to this position, it's blocking star A. Right, and so we're getting all of the light from star B, but only a fraction of the light from star A. And so the apparent brightness of the system decreases. And then star B passes and it goes back to being the maximum value, right? In this position, this is pretty much the same as the first, except star B is on the opposite side. And so we're getting the full brightness from both of them. And then star B passes behind star A, and we can only get the brightness from star A, and that's why we see a much more significant dip here. Oh, you know what? I actually have a link here. I was looking for this, and it turned out it was in my notes section of my slide. Let me open this up and I'll screen share it very quickly. All right, so while I'm pulling that up, this kind of star system, this eclipsing binary, is when we are observing the two orbiting stars along the plane in which they're orbiting each other. All right, so let me share this screen. Here we go. And I'll zoom in on this. Ooh, too much. There we go. All right, so we're looking at the total brightness as a function of time. There's a red dot in the middle, so we can see like what our perspective is. If something's behind the red dot, it means it's farther away. If something is in front of the red dot, it means it's closer to us. All right, so we can see like right now, the blue star is closer, and now the blue star is farther away. And now the blue star is closer, and now the blue star is farther away. All right, and so in tracking that total brightness of time, we see that we get a big dip and then a little dip. And then time passes and we get another big dip. And then we'd get another little dip. Right? And so this is an eclipsing binary, right? Again, so we're looking at it along the plane of their orbits. Okay, back to our PowerPoint. Okay, there we are. All right, so there's our eclipsing binary. Then we have a spectroscopic binary. So here, what we're seeing is, in this case, we're looking at star A, which is very, very massive, which is why it pretty much stays at the center of star B's orbit. Star B is orbiting around star A clockwise from this perspective. And then all the way on the right, somewhere down here is a telescope on Earth. And from this, this telescope would be much farther away. And we can track the light and the spectrum of the light that's coming from star B and star A, if star A happened to wobble also. But this is very similar to the wobble method for detecting an exoplanet, except we're using it with stars here. Right? So we're using Doppler shifting to basically measure how fast the stars are orbiting each other. Right? And from that, we can get information about their masses. And I'll show you another short GIF, which is on a different tab in this window. Here we go. Okay, so let's just take a moment so you can really internalize what you're seeing here. Here's a binary star system. Both star A, the blue one, and star B, the red one, are orbiting each other around some center of mass. Right? And this green point over here represents our telescope on Earth. We are observing these stars from a great, great distance. And we're recognizing that both stars exhibit Doppler shifts, and their shifting opposes each other, because as one star moves towards us, the other star moves away from us. Right, again, as one star moves towards us, the other moves away. Right, so when one of the stars, let's follow the red one because it's the most obvious to see on the bottom. When the red star moves towards Earth, we should see that it gets shifted towards the bluer end of the spectrum. It's moving towards us. The wavelengths are decreasing, the frequency goes up, and we get that blue shifting. And when it moves away from us, we see that the spectrum is headed towards the red end of the spectrum. We're getting redshift because as it moves away, the wavelengths are being expanded and the frequency with which they arrive at our location decreases, right? And we can sort of make sense of that with the blue star, star A as well. And so all of this is to say that it is possible to determine the period of their orbit around each other. And using that information, we are able to determine their masses. All right, let's get back to the PowerPoint. Sorry, I'm bouncing back and forth so much. I don't usually toggle so often. Okay, so let's just summarize what we've learned so far. Summarize some of the things that we've said. This is also covering some of the stuff from the earlier lecture. Right, so how is it that we measure stellar luminosities? Well, if we know how bright a star appears from where we are observing, and we know how far away that star is from us, then we can figure out the luminosity, the power output of that star. Right, using things like the inverse square law, of which light adheres to. You know, we can get an idea of a star's absolute brightness. Right, and we can also use stellar parallax to determine how far stars are from us. Right, so we're able to calculate how much the stars shift across or with respect to the distant background stars. And we know our distance from the sun, right? And we can figure out sort of what shape we're getting between us, the star, and our sun. We can use a little bit of trigonometry to figure out what the distance to that nearby star would be. Right. When it comes to measuring stellar temperatures, however, right, there are two things that we can look at. For now, let's just focus on color. We'll come back to spectral type later. But a star's color, right? We already discussed how things that are hotter, right, tend to exude bluer light, and things that are cooler tend to radiate redder light. Right, so the hottest of stars are blue, and the coolest of stars tend to be red. All right, how do we measure stellar masses? Well, we can use Kepler's third law, to get the total mass of a binary system. We can measure the orbital period. We can figure out how far apart the two stars are from each other, all of which is to say that we have a means of getting the masses of those stars. Right? We're not too focused right now on what that exact process is for getting the mass, what those calculations are, but just to know that there are ways of calculating the mass. Right, so just we can skip this. I already answered some of those questions. All right, so I'd like for you to take a moment, and I want you to type an answer and prepare to hit enter in the chat box, but don't send it yet. All right, just take like a minute or so. All right, and think about what you could learn about human life by looking at one family photograph, right, where you can see multiple generations of a family. Right. Think about what you could learn. All right. Type a response into the chat, but don't hit enter yet. I'll let you know when to hit enter, and you'll all press it at the same time. Take about 30 more seconds. All right, let's hit enter and see what you came up with. Okay. So what could you learn about a human life by looking at a single snapshot of a large family, including babies, parents, and grandparents? It takes time and patience. Well, that might be hard to discern from a single picture, because you don't necessarily know how much time it takes for a child to become an adult, to become an elder person, unless you're just saying from the perspective of actually being a human that you're able to do that. But maybe we get an idea about the life cycle. Okay, maybe we get an idea about life cycle. All right, maybe you can learn a little bit about genetics. All right, you might be able to identify certain traits that are hereditary and ones that are not. So you could learn about your history and existence. You could use the past to reflect on things that will impact you in the future as well. Okay, and that seems like a lot to be able to get from a single snapshot. Right? So to be able to learn about your history, that's like saying that the snapshots is the equivalent of, an encyclopedia or something of the like. So you can learn about culture and customs. Yeah, you might be able to get an idea. But if you only have one picture to look at, how much culture and how many customs are you really going to be able to capture? You can also tell the time period the picture was taken in, most likely. Okay. Again, if that's maybe that's if you know a thing or two about humans. But if you don't know a thing or two about humans, that might be a little bit difficult. Now, the reason I asked this question, and this seems, how does this in any way relate to astronomy, is I want you to think about how this might be similar to when scientists study stars. Is it similar? Do you see any kind of comparability there? Again, let's type an answer into the chat. Let's just say that there's no right or wrong here. So however you answer is totally fine. All right, but let's see. How many of you, just a quick yes or no in the chat, quick yes or no will do. How many of you think that there is something similar here? There is a comparison to be made about scientists studying stars and looking at a snapshot of a single family. Yeses and nos. Let's see them in the chat. Okay. All right, we've got a couple of yeses and a couple of silent responses, aka no responses. So I'd reckon that there is probably a bit of a similarity here, right? Because when you look at a single picture, right, within the picture, right, you're not really seeing much in terms of the aging of the family members, right? You're getting what they look like at a particular point in time. When you think about the lifespan of a person, what's the average lifespan these days? Somewhere in the high 70s, low 80s. right? Average human lifespan.
I know for the average New Yorker, it's 81.2 years.
All right, I'll take it. The average New Yorker means I got a good 51 years ahead of me. I'm happy about that. So what about the lifetimes of stars? Stars live around 81.2 years. Does that sound about right?
They live for way longer than that.
Yeah, they do. They live for much, much longer. And so the rate at which stars change is so much slower, right? Because their lifetimes are vast in comparison to ours. And so we really, like, when we look up at the night sky, we're really kind of just looking at a snapshot of what the universe looks like in this moment. And even over the next, 50 to 100 years, like, not too much is going to change. I mean, I don't want to make it sound like there aren't things to look at. There's always, there are always things happening, and things to study. But, much of what we're seeing will not change very dramatically in the short term. And that's kind of the point here, right? And that means it's a little bit, for scientists trying to make sense of what the life cycle of stars is like, it's kind of like looking at a picture of a family, right? Where you can't actually see the transition from baby to parent to grandparent. But you know that those stages are there. And so when we look at stars, we spend time classifying them, and this helps us make sense of what their life cycles will be. So let's start by looking at what's called a Hertzsprung-Russell diagram. That's a bit of a mouthful, so often we will just abbreviate it to an HR diagram. And what we're seeing here is a diagram that on the x-axis, plots temperature, and on the y-axis plots luminosity. Right, so on the x-axis, we have surface temperature. All right, again, for those of you that had a chance to watch the earlier lecture, it's a little bit weird, but temperature increases as you go to the left. Right, oftentimes when we look at graphs, we tend to think that the values increase as you go further and further to the right. Here it's the opposite. And on the y-axis, we have luminosity measured in solar units. So basically, how do the luminosity of these different stars compare to the luminosity of our sun? All right, so let me see here. Our sun should be directly in line with a luminosity of 1, being that we're measuring this in terms of solar units. Right, so our sun would have a luminosity of 1 solar unit. And if we go slowly but surely, so I don't make too much curvature in my line, right? Right here it says sun, and our sun is right there on this diagram, right? And just following up what was said earlier, that if we follow this down on the y-axis all the way to the bottom, right, our star is a G spectral type, right? Which puts it, our star's temperature is somewhere around 5,800 Kelvin. So that seems to be just about in the right spot there. Okay. As we go up on the y-axis, right? I know it's hard to see because the font is very small, but we're going from 1 to 10, 10 to 100, 100 to 1,000, 1,000 to 10,000, 10,000 to 100,000, 100,000 to 1,000,000. All right, so anytime you go up or down, the luminosity changes by a factor of 10. All right. So we can make a little note of that to ourselves. All right. We have different sections on this diagram, on this chart. So the first one that we're going to be looking at is this section here called the main sequence. Right. We also have a section referred to as giants, supergiants, and white dwarfs. Right. These are some that we're going to be looking at. Right. All right. Most stars in the universe fall somewhere on this diagonal that runs from the top left to the bottom right. Again, this is called the main sequence. All right. Also, while we're on this slide, make note, because I don't think I have it in the slides further down, that it's indicating here the masses of the stars in terms of our sun's mass, in terms of solar masses. So like our sun, let me just get the laser pointer out. Our sun has a mass of 1 solar mass. But a star down here is only 3/10 the mass of our sun. And this is 1/10 the mass of our sun all the way down there. And as we climb further up the main sequence, we go 1.5 solar masses, 3, 6, 10, 30, 60 solar masses. And we see that it really increases quite rapidly as we get to that top left section. On the underside of the main sequence, we also have the lifetimes of these stars. Right? And the lifetime here is being described in terms of different powers of 10 and years. So 10 to the 10 years, we're talking about around 10 billion years. So our sun will have a total lifetime of about 10 billion years. Right? Going a little bit further down, a star that's around here, maybe that's 0.5 solar masses, might have not 10 billion years, but 100 billion years, right? So a star down here is going to live 10 times longer than our sun. While a star that's up here, somewhere around like 2.25 or so solar masses, assuming that well, let's not assume anything. Let's just say a star around here is going to have a lifetime of about 1 billion years. So that's going to live 10 times shorter lifetime than our sun will. This is going to be 100 million years, right? So this is going to be this star. It's only 6 times as massive, but it's going to live 100 times smaller of a lifetime, right? Or 1/100th of our sun's lifetime. And then you get all the way up here, and it's like 10 to the 7, right? And that's 10 million years, right? So here are these really massive stars that are only going to live for about 10 million years. Meanwhile, our sun's going to live for about 10 billion. So our sun will outlive these ones by about 1,000 lifetimes, 1,000 of their lifetimes, right? So there's a lot of information here, right? Stars on the bottom right, lower mass, longer lifetimes. Stars on the top left, larger mass, shorter lifetimes. Okay. So in addition to spectral type, we also have luminosity class. We're not really going to dig too deep into that, but if you are looking up stars, and I know that for last week's discussion prompt, where you had to do a little bit of research on a star in the constellation of your zodiac sign, you might have looked up some of this information. So just be mindful that when you look up these classifications, right, you're looking at the spectral type of our sun, which is G2, and then the Roman numeral 5 that comes after it indicates that it's a main sequence star. Whereas Betelgeuse is an M2 spectral type, meaning it's not as hot as our sun is. but it is a supergiant. All right, it's a much larger star. Okay, moving on. All right, so we need to know a couple of things about HR diagrams. One, we can get information about the temperature of these stars, right? Stars that are plotted on here. There's information about color, right? If you look at the bottom axis, and also if you look throughout the diagram, you'll see that there are colors associated here with the different spectral types. So O, B, A, F, G, K, M, where M is the coolest spectral type in terms of temperature, and O is the hottest. So M stars are red usually. O stars are a very, are blue, very, very blue. And then in between, we have stars that are lighter blue, kind of orange, yellow, white, so on and so forth. All right, so we can get information about temperature. We can get information about color. We've got spectral type on the bottom. Remember that knowing the spectral type would also indicate what kind of absorption spectra we would expect to see coming off of these stars, and we can get a little bit of information about what's in their atmospheres. We can get information about luminosity on the y-axis, right? And then on these diagonal lines, which we don't always see when looking at HR diagrams, right? Not all HR diagrams are displayed exactly the same way. We also get some information about size, right? The radius of these stars. And it's very hard to see. So I'm just gonna, I wonder if there's like a magnifier. No, there's not. On the line right over here, let's get the laser pointer out. On this line, this says 1 solar radius. So our sun should fall right on this diagonal, and lo and behold, it does. Our sun is right here underneath my laser pointer. But if we go down, every one of these subsequent diagonal lines is 10 times smaller in terms of radius, which means that we're going to see a significant change in the volume or the overall size of these stars. And as we climb this sort of diagonal ladder, the size of the stars is increasing by, rather the radius is increasing by 10 times. All right, so we've got 4 positions labeled on this diagram, right? A, B, C, and D. And I want you to take a moment. You can type your answer into the chat, right? Don't hit send until I give you the signal. Which of these stars is the hottest? What do we think? All right, get ready to type your answer in, or type it, but don't hit enter. 10 more seconds, 10 more seconds. 8, 7, 6, 5, 4, 3, 2, 1. Hit enter. Wow, which one? What did you say?
Which one did I say? I meant to say B.
Yeah, you meant to say B. Interesting. So we're getting a couple of different answers here. We're getting some A's, B's, C's, and D's. Okay, so if we're talking about which star is the hottest, what is there another way? How could you rephrase this question? What's another way of asking the same thing? James, could you put it into different words for us?
What was your question again? How to like?
Which star is the hottest? Can you rephrase that for us?
What star has the highest temperature?
Okay, very good. Where on this diagram are we looking for temperature? Where does it show temperature on this diagram?
On the bottom.
On the bottom, right? So temperature increases as we go further and further to the right. So of these 4 letters, which one is the furthest to the right? Yeah, that's going to be A, right? So don't be misled here by the fact that it's a white dwarf, right? That it's a smaller star than the supergiants and star D, which is on the main sequence, right? Star A is the hottest star of the four that are labeled, right? Star A is the hottest. Let's try another one. Maybe now we'll get the hang of it. Which star is the most luminous? Ooh, I don't know why it didn't copy the right image. All right, I'll come back to it. Which star is the most luminous? A, B, C, or D? All right, let's just go ahead and type our answer into the chat. Most luminous, most luminous. Ian and Mario say C. Does the rest of the class agree? Do we disagree? Is C the most luminous? Or is it B? I don't know, maybe it's B. Could it be A? Anybody think it's D?
Do you mind if I ask something?
Of course I do not mind. What is your question, Ian?
Does temperature at all make one of these stars more luminous than another one, even if on the luminosity scale one of them is higher?
Does temperature make a star more luminous? So if we have two stars that are the same temperature, but one of them is bigger, the one that's bigger is going to be more luminous.
I see.
Do you follow the logic there, Ian?
Yeah, I do.
Okay. The correct answer for which is most luminous is C. All right, C is the most luminous. C was somewhere around here because C is the highest up on the diagram, right? It is the farthest up on the y-axis where we are measuring luminosity. All right, I'm going to go back, but the next question is, which is a main sequence star? A, B, C, or D? Which is main sequence? Lightning fast, folks, lightning fast. A, B, C, or D, which is a main sequence star? Ian and Mario, you guys should get bonus points for being the fastest to answer.
Thank you.
You're welcome. It's the supreme intelligence. Okay. All right, James, Nicole joining the fray. Everyone's saying D. D is correct. All right. D is a main sequence star. And last but not least, which star has the largest radius? Which star has the largest radius? A, B, C, or D?
Would you mind reviewing the stars without the letters?
Sure. Like this, Ian?
Yeah, but never mind. I thought it would help.
Nope. Which has the largest radius? Yeah, A through D are hypothetical stars, Mario. Right, so well, no, you can tell based on where I've positioned the letters. You can tell based on where I've positioned them. Yes, it is star C. All right, so remember, we've got these like diagonal lines here indicating solar radius. And the higher we go on these diagonals, the larger the stars get. And you can also see that from the pictures here, that the trend is increasing radius as we go up towards from the bottom left to the top right of the diagram. Which of these stars? So which of these stars is the coolest? Which of these four stars here is the coolest? Okay, we've got a couple of C's. James says D. Dylan says B. Jeraine says D. Oh, get out of here, Ian. Your Leo DiCaprio jokes. Which star is the coolest? Well, again, now we're talking about temperature, right? We're talking about temperature. So we need to be looking at that horizontal axis and seeing which of these letters lines up with the cooler end of the temperature axis. And that would be star C, right? If we follow star C all the way down, or we would see that it is in the lowest end of the temperature range of these four choices. And so A is the hottest, C is the coolest. C is the largest, A is the smallest. D is a main sequence star. Based on where these four are, C is also the most luminous. A is the least luminous. But I think that a lot of people, look at this and they get thrown off, even though the information is so there, it's so in front of us. There's a lot of stuff to look at here. And as first time observers of this diagram, it might be a bit to take in at once. Don't be thrown off by the fact that C would be the largest of these stars. It can still be cooler in terms of its surface temperature. So let's move on now. Okay, so what makes a star a main sequence star in the first place, right? What does that even mean, right? Supergiant, giant, white dwarf, that kind of makes sense because we're categorizing them based on their size and or color. But what makes something main sequence? Well, it has to do with what's going on in the core. Earlier, we talked a little bit about how, stars get their energy from nuclear fusion that's happening in their cores. And nuclear fusion could mean that, we're fusing hydrogen atoms together. It could mean that we're fusing helium atoms together. It could mean that we're fusing carbon atoms together, so on and so forth. But a star belongs on the main sequence if and only if it's fusing hydrogen into helium at its core. All right, that's the only thing that makes something a main sequence star. It has to be fusing hydrogen to helium in its core. Right, and again, just to follow up, the most luminous main sequence stars, so this is the main sequence. Luminosity increases as we go up on the y-axis. The most luminous, the ones with the greatest power output, are the blue main sequence stars. They are the hottest main sequence stars. The least luminous are the reds, oranges, and the yellows, right? Really, it's the reds that are the least luminous. They're the furthest down on the y-axis. And again, these are red, right? So there's a relationship there between color and luminosity. And if at a distance you can determine if you could figure out the color of a star, that might be helpful in determining the star's luminosity. It might be helpful in determining the star's temperature. But I mean, there's obviously more to it than that, but it's useful information to have. All right. As we discussed, the mass of stars on the main sequence can vary widely, right? From 0.1 solar masses and smaller. Excuse me. I don't know what it is. I think it's the headphones that make me yawn so much. There's something about having headphones on that my brain just, it's like go to sleep. And then we have these high mass stars with 60 solar masses, so on and so forth. All right. And as I mentioned earlier, the mass of these stars is the most important aspect of determining what their futures are going to be. Or why is mass so important? Why is that? Well, the mass of the star is what's going to determine, you know, where that stability is in terms of the energy that's being generated at the core and the energy that's being released at the surface, right? A star is stable when that energy balance is, or when the input and output of energy is balanced, right? And so the single most important quantity that affects where that balancing point is mass, right? It's very, very sensitive to mass. You know, so for example, just to give you an idea of just how sensitive, a star that has 10 times more mass than our sun does would be 10,000 times brighter, right? Not 10 times brighter just because it's 10 times more massive, 10,000 times. Excuse me, I shouldn't be saying brighter, I should be saying more luminous. Right, so the power output of these stars that are 10 times more massive would be 10,000 times the power output of our sun. All right, which means it only takes a little bit of a difference in mass for luminous intensity to change by a large amount. Right, this is not a linear relationship here that we're looking at between mass and luminosity. All right, so because it's not a linear relationship, right? Because larger mass means that there's going to be a higher luminosity, right? We're also going to get a higher surface temperature, right? So that we're getting more power output, right? We're getting more energy radiated away at the surface, and that's what causes them to be to have so much power output, right, at their surfaces, right? Is that there's just much hotter temperatures, right? And that's why we have these very the most massive stars of the main sequence. If I go ahead to the next slide, I'll just pull up the HR diagram again. Right, the most massive stars are blue. Right, they have so much mass that their luminosity, their energy output, has to be significantly higher than that of our sun. And so while the stars at the top here might only be 60 times more massive, their energy output, their luminous, their luminosity is way, way larger. Not 60 times greater, but I don't know the exact number off my head, but certainly more than 10,000, right? Because if 10 times the solar mass means 10,000 times the luminosity, then 60 solar masses would be even larger than that. And so to be able to have so much power output, they have to be hotter at their surfaces, and that's why they appear bluer. Gosh, my brain is just melting, folks. On the other end of the spectrum, right, we have these redder, lower mass stars, right? Because they're so much lower in mass, their energy production, right, the rate at which energy is produced is much lower, and so the energy output is less, and so they don't have to get as hot to reach their balancing point. And so maybe I should have mentioned that with the bluer, the hotter, heavier stars, because they're so much more massive, the pressure on the core, the stars, trying to collapse under its own gravity, really increases the rate of nuclear fusion, which increases the energy output at the star surface. Right, so just to touch on this a little bit, lifetimes along the main sequence. So a star will stay on the main sequence for as long as it has for as long as it has hydrogen in its core. But that means that they don't stay on the main sequence forever. Right? Eventually, main sequence stars leave the main sequence and evolve or follow a life track that brings it into like the giant part of the diagram, or the supergiant part of the diagram, or possibly even the white dwarf part of the diagram. Right? But stars do not stay on the main sequence forever. Right? And what these lifetimes, what these stellar lifetimes look like really depends on how much mass the stars start with. So when a star forms and it starts its journey on the main sequence, its fate is already sealed, right? You could predict almost exactly how long a star will last based on how much mass it starts with when on the main sequence. Could you imagine that? Seeing a newborn baby, taking one look at it, or holding it in your hand and feeling its mass and saying, ah, yes, this one's got a good 70 years on it. Or this one's only going to make it to 57, or I don't know. That would be crazy. But with stars, we can do that, right? Because the mass of the star is what's going to determine the rate at which it uses its nuclear fuel, and its nuclear fuel is limited. So we can predict when the star will end its life cycle, or restart its life cycle. We'll get to that. All right. So again, just I'm reiterating myself a bit, but the more massive stars that are on the upper left-hand side tend to have shorter lives, and the smaller, redder main sequence stars on the bottom right of the HR diagram tend to have much longer lives. Right. Again, it just has to do with the rate at which nuclear fusion is occurring, right? The nuclear fusion of hydrogen into helium. Right. Recapping that, just because a star has 10 times as much mass as our sun doesn't mean it's going to be 10 times more luminous. Right? It's not a direct relationship. It would be 10,000 times more luminous, and that should say a lot about stars that are even more massive than that. All right, so those stars that are 10 times more massive are 10,000 times as luminous, and therefore are using up their nuclear fuel at 10,000 times the rate that our sun does. Okay, so to summarize, high mass stars tend to be higher luminosity. Again, this is specifically for stars on the main sequence. Right, we're specifically talking about stars on the main sequence. Higher luminosity, shorter lifespans, right? Larger radii. Right? We're talking, so they're bigger. Right? They are bluer. And again, this is all for stars on the main sequence that have high mass. Then we have stars that are low mass. And we could probably figure out what's going to go on this list just by looking at the list for high mass. Right, low mass stars would have a low luminosity. They would have longer lifespans, smaller radii, and they would be redder. They would be redder. So let us, again, in summarizing what we just discussed here, just taking it back a little bit. A Hertzsprung-Russell diagram, right, is a diagram plotting luminosity of stars versus their surface temperatures, or color, or spectral type, because those three things are directly tied to each other. Right, to be on the main sequence means that a star has hydrogen fusion into helium at its core, right? That's not true of all stars. Not all stars have hydrogen fusion going on in their cores. And we'll explore that probably next week. And we have that in terms of plotting the stars along the main sequence of an HR diagram. We're going to take careful note of their masses, right? That stars with higher mass, more luminous, bluer, larger radii, shorter lived. Stars with lower mass, much redder, less luminous, longer lifespans, smaller in size, so on and so forth. All right. This is where we're going to stop for now. And then I'm going to stick around to answer any questions that people have about the space mission assignment, or if there's anything else that anybody would like to talk about. I'm happy to take any questions from you. If you want to head out now, you can. If you want to stick around, you're more than welcome. All right, but that's going to be our lecture for tonight. Make sure that if you didn't already watch, hold on one second. Make sure that if you didn't already watch the earlier lecture, that you do watch it, because it does cover a lot of important stuff that we need to know. All right, and with that, have a good night, folks.